Welcome to this session on the relational model in DBMS, a fundamental concept in modern database design. Whether you are a student just learning about databases or a developer aiming to master SQL, understanding the relational model is essential. In this presentation, we will take a deep dive into how data is stored, organized, and related using tables, which we will refer to as relations. The relational model is the basis for most relational database systems like SQL, MySQL, Oracle, SQL Server, and etc. This model was proposed by E.F. Codd in 1970 and it revolutionized how data is managed in computing. Instead of storing data as flat files or in hierarchical formats, the relational model treats data as sets of tuples arranged in tables. We will also explore how keys ensure uniqueness, how constraints enforce data integrity, and how this model supports everything from basic queries to complex reporting systems. So, whether you are preparing for an exam, a job interview, or simply want to understand how enterprise systems store their data, you are in the right place. Let's begin by looking at the agenda for this session. Here is what we will cover in this presentation on the relational model in DBMS. Relational model concepts. We will start with the origins and fundamentals of the model, how it organizes data into tables, and why it became the standard. Components of a relational, you will learn what a relation really is and how it breaks down into rows, tuples, columns, and domains. Keys and constraints. We will explore keys like primary, foreign, and candidate keys. Then we will dive into constraints, rules that protect data accuracy. Properties and advantages. What makes this model powerful? We will discuss its benefits such as simplicity, logical structure, and supports for powerful queries. Summary and example at the end. We will walk through a sample database structure to tie everything together and give you a real world example to practice with. Ready? Let's begin with an overview of the relational model and how it was developed. Relational model overview. The relational model was introduced by British computer scientist E.F. Codd in 1970 while working at IBM. It was a breakthrough that shifted how data was handled in computer systems. Prior to the relational model, data was stored using hierarchical and network models, systems that were rigid, difficult to scale, and harder to modify. Codd proposed a model based on set theory and first order predicate logic. In this model, all data is represented in the form of relations, which we know commonly referred to as tables. Here is why this model becomes so popular. It uses simple two-dimensional table to represent data. Each table has rows, means records, and columns, means fields, which makes data easy to read and query. The structure allows for mathematical operations and logical reasoning to process information. Relational databases based on this model include industry giants like MySQL, SQL Server, Oracle, and many others. The key strength of the model lies in its declarative nature. Users specify what data they want, not how to get it. This leads to more flexibility and better data independence. Let's now break down the main components of relation, the foundation of this model. Components of a relation. Let's break down the structure of a relation or what we typically call a table. A relation represents a real world entity such as students, courses, or orders. Each row in the table is called a tuple, and each tuple represents one instance of that entity, like a specific student or a particular order. The columns are called attributes. Each attribute holds a particular piece of data, like a student name or an order date. Lastly, we have the domain. This refers to the set of valid values for a particular attribute. For example, if you have an age column, The domain might be all integers between 0 and 150. These components together define how data is stored in a structured and meaningful way. Properties of relations. Now let's look at the unique properties that define relations in the relational model. First, each relation has a unique name. You can't have two tables called employee in the same database schema. Next, rows are unordered. The ordered in which records are stored doesn't affect the data, unlike spreadsheets. Also, column values must be atomic. This means each field contains only a single value, no lists or nested data. Lastly, every attribute belongs to a domain, which keeps data consistency by restricting what values are allowed. These properties help maintain clarity, consistency, and efficiency in how we organize and retrieve data. A superkey is any combination of attributes that can uniquely identify a row in a table. For example, in a student table, both student ID alone and the combination of student ID and email can serve as a superkey. It's important to note that a superkey may include extra attributes. It doesn't have to be minimal. Superkeys forms the basis for identifying more refined keys, like candidate keys, which we will look at next. Candidate key. A candidate key is a minimal superkey. That means it has no unnecessary attributes. In any table, there may be multiple candidate keys. For example, both student ID and email could uniquely identify a student. Out of this, one is selected as the primary key while other are kept as alternatives. Candidate keys help us enforce data uniqueness without redundancy. Primary key. A primary key is the candidate key that chosen to uniquely identify tuples in a table. It must be unique and not null for every row. For example, student ID might be the primary key in the students table. Every table should have only one primary key. Though it may consist of multiple attributes in some cases, a composite key. It is the cornerstone of maintaining data integrity in a relation. Foreign key. A foreign key is an attribute in one table that refers to the primary key of another table. It's used to establish relationships between tables, such as course ID in a student table referring to the courses table. Foreign key ensure that data stays consistent across tables and help enforce referential integrity, which we will cover shortly. Overview of integrity constraints. Integrity constraints are rules that ensures the validity and consistency of data in a database. There are three key types of constraints: domain integrity, entity integrity, referential integrity. Domain integrity ensures values are within the allowed set. Entity integrity ensures each row is unique and identifiable. Referential integrity ensures foreign keys match existing primary keys. These rules help protect data from errors and ensure accuracy throughout the system. Domain integrity. Domain integrity ensures that values entered into a column are valid and appropriate. For example, a salary column should only contain positive numbers, and a date of birth field should only have date values. This is enforced using data types, constraints like check or default values. By enforcing domain integrity, we prevent incorrect or corrupted data from entering the database. Entity integrity. Entity integrity is about making sure that each row in a table is uniquely identifiable. This is achieved through the primary key. A primary key must never be null, and every value must be unique. Without entity integrity, we could end up with duplicate or ambiguous records, which leads to confusion and unreliable queries. Referential integrity. Referential integrity ensures that relationship between tables remain valid. It requires that foreign key values in one table must match primary key values in the reference table. For example, if a student table has a course ID as a foreign key, There must be a matching course ID in the courses table. If the courses is deleted, the database must either prevent the deletion or cascade the change to maintain consistency. Violation of integrity constraints. Violation of integrity constraints occurs when data doesn't follow the rules set by the system. Example include trying to insert a null value in a primary key field, entering a value outside the allowed domain, using a foreign key that doesn't match any existing value. These violations are usually blocked by the database systems to preserve accuracy and consistency. Benefits of using constraints. Why use constraints? Because they offer many benefits. They enforce business rules automatically. They prevent incorrect or inconsistent data. They reduce the need for manual check in application code, and they help ensure data quality across large systems. In short, constraints are like built in safety guards for your data. Advantages of relational model. The relational model offers several powerful advantages. It is simple using family table structures. Based on strong mathematical principles, it enables efficient query using SQL, and it supports data independence, meaning the physical storage can change without affecting the logical structure. This is why relational databases have stood the test of time. Limitations of relational model. Of course, no system is perfect. The relational model has some limitations. It may not perform well for unstructured or semi structured data like documents or images. Complex joins can reduce performances in large databases. It often requires normalization, which can make queries more complex. Still, its strengths make it a popular choice for most structured data applications. Relational model in practice. The relational model is used in all major relational database systems. MySQL, Oracle, SQL Server, and many other rely on this model. It underpins enterprise systems like ERPs, CRMS, and e-commerce platforms. Its consistency and structure support complex queries, reports, and transaction systems. Mastering this model is essential for any database or backend developer. Design example. Let's look at a practical example. Suppose we have a student table with columns like student ID, name, age, and course ID. Then we have a course table with course ID, course name, and credits. The student dot course ID acts as a foreign key referring to the course ID. This relationship allows us to join the tables and fetch course names for each student, demonstrating how foreign key works in practice. Wrap up. Let's summarize what we have learned. The relational model organizes data into structured tables. Keys ensure uniqueness, while constraints ensure data validity. The model is the foundation of modern relational databases. Understanding this model gives you a solid base for mastering SQL, query design, and database architecture. Thanks for following along, and don't forget to practice with your own table designs.